So with the Zool basics out of the way, let's look at caching. Caching is fairly critical when you have a large number of microservices serving up largely static data, so let's explore our options. There are a number of opportunities for caching in our architecture, and the methods of caching that you choose are completely up to you. First, there is an opportunity between our client and our main API gateway entry point. In fact, if our client is a browser, we have caching capability built into the client. However, this HTTP-based caching capability doesn't work automatically with just the client capabilities. It's also up to the server to send the correct HTTP headers back to tell the client what it can cache and for how long. These headers are actually well known in the web development world. These are things like the expires headers and Etags. These are things that web developers have used for years on static content. We also have the ability to set up caching between our API gateway and the backend services, and if the services call each other, between them as well. Our services would need to populate the correct headers, and our HTTP gateway would need to respect them. One other opportunity is to use Spring's caching abstraction. It is a quick, clean way to implement method caching in your code for any purpose. I really like it, and I'll show you how to use it on the next slide, but I think for microservices, especially those using REST and HTTP, it's probably best to embrace the capabilities built into the underlying protocol in use. So, Spring's caching abstraction. For those of you who haven't seen this before, the Spring framework provides a very easy-to-use caching abstraction that makes method caching super simple. It's so easy. All you do is annotate methods with the @cacheable annotation, in which you describe the name of the cache and the key that you want to use to store data in the cache. Now separately, and I don't have it shown here, you define a bean to serve as a cache manager, and that tells the framework the backend implementation to use for the cache. Now out of the box, you get things like synchronized maps, which are available in the JDK, but it's also easy to plug in EHCache or Gemfire or whatever you're using as a cache. So in this example, I have a Fane client, but take a look at the @cacheable annotation on the getInventoryItem method. This is telling the framework that values returned from this method are eligible to be stored in the backend cache, specifically a cache called inventory, and more specifically under a key value of the SKU passed in as a method argument. Now, Spring doesn't do the actual caching. Instead, it just turns around and tells the backend implementation to cache the value, and it's up to the backend implementation to take care of storing and for how long. Now, the next time the getInventoryItem method is called with the same SKU value, Spring will retrieve the item from the cache and return it without actually executing the code in the method. So in this case, since this is a Fane client, we have just saved a remote call. Now, if this is new to you, you might have a dozen questions about how the data is stored and how long it stays in the cache and whatnot. Ultimately, it is up to the backend cache and how it is configured to answer these questions. And if you'd like to learn more details here, this is a good place to look at the Spring reference documentation. Now, the method caching abstraction in Spring works great for general purpose use, and I really like it. But for our microservice application, based largely on HTTP REST calls, there are some drawbacks here. Although I can configure the backend cache implementation to expire entries whenever I want, if I'm really embracing HTTP as an application protocol, I should really have the backend service, the warehouse service, make this decision. And the warehouse service should be able to do this by sending back HTTP headers for expires and the Etags. Now, a great option for HTTP-based caching is the so-called Etags. You can use the expires headers, but Etags are more sophisticated. Etags work like this. First, the client requests a resource. When the server returns the resource, it also sends back an Etag header in the HTTP response, and that header has a value associated with it. The value is typically a hash code, which has been calculated based on the response body content. The Etag uniquely identifies the response body content to both the server and the client. And both the server and the client would store the etag value associated with the URI and the content. Now, at a later time, if the client makes a request for the same resource, the same URI, it will send along the etag value within a different header called if none match. In effect, the client is saying, I would like this resource, and this key represents what you sent me last time. So if this key doesn't match what you sent me last time, please send me updated content. Now the server will do the exact same processing that it did before. However, before it returns the new response body, it calculates the hash on it. And here's the important part. If the hash matches what the client sent, the server knows that the client already possesses the content that was going to be sent. So there's no point in sending it again, and the server will send back a 304 return code. Now 304 is not an error. It literally means not modified. So this is the server's way of telling the client that the resource has not changed since the last time it was sent. The result is that no bandwidth is wasting sending the client something that it already has. Now, if the hash is different, then the server sends the content and it sends a 200 and it sends a replacement etag. So the purpose of the etag is to save bandwidth when the client already has a cached copy of what the server was going to send. All modern browsers support etags, and you can build your services to take advantage of them too. Now you may have noticed from my description here that the server side still had to do all of its normal work, and that this work was not avoided. And this is true. What I have just described to you is technically what we call a shallow etag, and it's only intended to economize on network activity. The holy grail of etags is something that we call the deep etag, which I'm not going to be able to show you. This is where the server can somehow make a determination before it does any processing that a 304 can safely be returned. So deep etags require a lot more thought and are really out of scope for our discussion, but it is something that you should keep in mind. Now on the server side, the Spring framework makes it super simple to implement shallow etags on any web application. It provides a servlet filter called the shallow etag filter, which you can install using the code you see here. A Spring Boot application will notice a bean of type servlet filter, like we have here, and it will automatically add this filter to the filter chain. The filter will calculate a hash value on the response body and return it on all responses. It also stores the original URL requested with the hash value. Now, if the request contains the if none match header with a hash value, it will double check before it returns to see if there is a match of the hash value that it already sent. If so, it returns a 304 with no content. Otherwise, it returns a 200 with a response body. So again, this is a shallow etag. It does not reduce server-side work. It only economizes network load between the client and the server. Now, let's take a look at the client side. After all, etags won't work unless the client is storing etags and sending if-none match headers. On the client side, we have Spring's REST template for making REST calls over HTTP. Now, unfortunately, this template does not supply etag handling out of the box. But the Spring team built an easy solve into this class. The template allows us to plug in the HTTP client, which is part of the Apache HTTP Components project. And the HTTP client supports etags just fine. So the code you see here demonstrates how to supplant the REST template's built-in HTTP behavior with the Apache HTTP client. With this installed, etags work automatically. Now, this code is something that you would configure once when you set up your REST template, and then you would dependency inject the template wherever you needed it. Now, you may be concerned that the REST template cannot make use of service discovery or load balancing, but actually it can, and this is described in the Spring Cloud Reference Manual. If you supply the REST template with a service ID rather than a URL to an actual host, it can automatically resolve the client using the usual mechanism and provide a load balancer when needed. So the REST template supports etags. What about Fane? After all, I spent a half hour of your time telling you how wonderful Fane is. Well, there is some bad news here. At the time of this recording, Fane doesn't work with Etags, at least not natively. And there really isn't a mechanism to plug in a different HTTP handler like the REST template. Now, Fane does have interceptors, and you might be able to plug different interceptors in there to do something like this, but it's definitely not something out of the box. Now, if you really want to use Fane, you could consider Spring's @cacheable method caching, or possibly exploring the framework or creating your own aspect to introduce it. And if you do come up with something clever, you might consider contributing it back to the Fane library itself. I'm sure it would be appreciated.